To better understand current flows in the ocean, we need to understand the effect of Earth's rotation in producing an angular velocity, omega, around the Earth's axis of rotation. This angular velocity is known as vorticity. Vorticity has a magnitude equal to 2 omega sine theta. Now, you don't have to worry about the maths too much, but the important thing about it is that at sine of 0 degrees, sine 0 degrees equals 0. So vorticity is 0 at the equator and is equal to 2 omega at the poles. So the strength of the vorticity increases as you move towards the poles in both directions. So when an object moves at a velocity across Earth's rotating surface, it tends to travel in a straight line relative to a non-rotating reference frame. This creates an apparent force that acts to the right of the direction of motion in the northern hemisphere and to the left in the southern hemisphere. This apparent force creates the Coriolis effect. In that acceleration, you can see the maths from the previous page is equal to 2 times the velocity multiplied by omega sine theta. So again, the value is 0 at the equator and increases towards the poles. So how does that influence currents in the ocean? Well, when wind runs across the surface ocean in this direction here we have a wind force, we have frictional drag across the surface, and that friction tends to make the water travel in the direction of the frictional drag across the surface. But because of the Coriolis effect, and this example here is given for the northern hemisphere, the water flow gets deflected to the right. So in the northern hemisphere, if we have a wind blowing in a direction like this, then we'll have deflection of the water flow out to the right. As we move down through beneath the surface to deeper layers in the ocean, the friction between this layer and this layer creates a frictional drag that makes the water tend to move in this direction. But again, because of the Coriolis effect, it's deflected out to the right again. And so on as we move to deeper and deeper layers. This ends up in what they call an Ekman spiral. So you can imagine that as you move deeper into the ocean with a strong wind blowing here, the motion of the water driven by the wind actually rotates around as you go deeper and deeper. This is known as an Ekman spiral. And the Ekman layer, which is the layer in which these spirals develop, is generally restricted to the top tens to hundreds of meters of the ocean surface, depending on the wind strength. For stronger winds, it'll be deeper. For weaker winds, it'll be shallower. The interesting thing about this is the total Ekman transport of water due to the wind is actually normal 90 degrees to the wind direction. So if you sum up all of these water directions in these layers and the total amount of water movement, if the wind is blowing towards the north, then the actual total water mass direction will be to the east in this example. So that creates some really interesting phenomena. In particular, upwelling and downwelling created along coasts due to this Ekman transport. For this example here, for the southern hemisphere, where we have a southerly wind blowing along a coast, so this would be relevant to the Western Australian coast, for example. The wind blowing along the coast in a south to north direction. Because we're in the southern hemisphere, we get a deflection to the west, to the left, and so the water will be moved offshore, and that creates a divergent flow, and as a result we have upwelling of water due to that divergent flow away from the coast. If we had a northerly wind blowing down the same coast in the southern hemisphere, the deflection of the water would be towards the coast, And so we would have convergent flow towards the coast, and we would have piling up of the surface water in a thicker layer on the coast, and that would then create downwelling. And here's a question for you to think about in your spare time. Is it likely to be warmer to swim on the south coast of New South Wales after a week of cold southerly winds or a week of warm northerly winds? The way to think about this is upwelling will bring up colder water, downwelling will actually bring in warm water from the East Australian coast further offshore. Here's an example from the South Australian coast. Here's a synoptic chart on the right, and here's a sea surface height diagram on the left showing variation in sea surface height due to the convergent flow of water onto the coast due to these strong westerly winds here circulating around a low pressure system in the Great Australian Bight. And here you can see the convergence produces water that is up to 30 centimetres higher in this particular case than it normally would be. So with this very strong winds, your high tide would be almost 30 centimetres higher than it otherwise would be. So these sorts of wind-driven convergent and divergent flows on coasts are really very important for all sorts of reasons. In this example here, also in South Australia, during summer and autumn, we often have these southeasterly winds that blow along the coast in this direction. And those southeasterly winds result in divergent flow away from the coast. So the surface water is deflected out to the west, to the left, and that creates upwelling. And you can see that upwelling in this picture of the sea surface temperature here, where the blue temperatures are 14 to 15 degrees, and the reds up here are around about 23 degrees. As a result of that upwelling, we bring nutrients up from depth. We end up with very strong phytoplankton growth and lots of primary productivity that support fish life and other higher organisms in the food chain. And this is one of the few places in Australia where you can go regularly to find blue whales, which come here, particularly during those autumn months, to feed on those plankton. And there's even a special festival, the Bonney Coast Upwelling Festival in Portland every year. On a much larger scale, the divergent flow away from the coast produces very strong upwelling that actually drives the total overturning flow of the ocean. As you saw on the Perpetual Ocean video, around Antarctica, there are very strong westerly winds, and they actually drive the very strong circumpolar current that flows from west to east around Antarctica in this direction. As the winds blow across the surface, they deflect the surface waters to the left, to lower latitude towards the equator. It's depicted here where the winds here are blowing into the page. The surface water is deflected to the left, and that creates very strong upwelling from very deep in the ocean up to the surface. As that surface water is pushed towards the equator, it's colder and more dense than other water that's flowing southward from the equator. So because it's denser, it goes underneath that water flowing along the surface from further north. So this creates this overturning, very strong overturning circulation in the deep ocean. And that can be seen here on this profile that runs total length from the far South Atlantic up to the North Atlantic. So here we have the winds, in this case, coming towards us out of the page, and the deflection to the left of the surface water masses produces this flow where this water is driven to lower latitude, and because it's slightly denser than this other water that's flying towards the south from the equator, it goes under it in this direction, and this water here upwells from very deep, from 3,000 or 4,000 metres depth in the ocean all the way to the surface And this is what creates this massive overturning circulation of the ocean, just simply this wind effect of the strong westerly winds circulating around Antarctica.